And then we will start working out some examples of projectile problems where we're not just being launched horizontally. What do we use? We use a little stomp rocket, right? Last Tuesday? Yeah. Except what? Really? Oh, wow. But we did that because we wanted to start looking at projectiles where we launched it from the ground up at an angle and then it came back to the ground. So we have our full parabola instead of just half of our parabola. And if I remember correctly, we did pick like a slightly different combination of 7 variables that we would always know for this type of problem. Does that ring a bell or like? Okay. So some of them are still the same, but a couple of them are slightly different. So the initial horizontal position we still call 0 meters, right? Just by default, we're going to start this thing at a horizontal origin and make it go off in the positive direction. So that's still true. The initial time is still 0 because it's still silly to start our stopwatches on anything other than 0 seconds. Our horizontal acceleration is still 0 because if it wasn't, it wouldn't be a projectile. So really our differences were only in our vertical column. So our initial vertical position is now 0 meters. That's different from before because we're calling the ground a vertical position of 0, right? And then up is our positive direction. So we are starting at a vertical position of 0. We're also ending at a vertical position of 0. Our initial time is still 0 seconds, right? It's always the same horizontally and vertically. Our initial vertical velocity is not 0 anymore. We're not launching horizontally. This has some vertical speed right from the start. So we don't know what that is. And then our vertical acceleration is still negative 9.81 meters per second squared. So we still have 7, it's just a slightly different 7, right? We used to say that we knew this one, we don't know it anymore, and we used to not know this one, and we do know that one. Were there follow-up questions from anybody about these 7 variables that we kind of generically know so long as we're launching something from the ground and then landing back on the ground? All right. So one of the pieces from a few weeks ago that we're going to need to remember now is how to do components of a vector, right? In some of these problems, we'll be given a combined speed, initial speed, and then we'll need to split it into a horizontal and a vertical piece. So here's an example of that type of information, right? We kick a soccer ball from the ground and we give it an initial velocity of 18.4 meters per second at 22 degrees above the horizontal, right? That could be all the information that we're supplied with, and that would be enough to solve for everything about this projectile problem. So let me just review with you guys how to do that, and then we'll look at some of the other pieces of these. If we're splitting a single vector into its components, we need to draw a right triangle where this is the hypotenuse. All right, so here we go. Right, there's the 18.4. I'm going to draw a horizontal leg of the triangle. I'm going to draw a vertical leg of the triangle. So 18.4 meters per second is the hypotenuse. 22 degrees is this angle here. The horizontal side of the triangle will represent the horizontal velocity, and then the vertical side of the triangle represents the initial vertical velocity. I don't need to say an initial horizontal velocity because that stays the same the entire time. Right, so we actually did this before like our last test, a while before our last test. Follow-up questions from anybody on the right triangle that I drew here? All right, and then to solve for those two sides, we just need to use our trigonometry functions. So if we want to solve for the horizontal part of the velocity, that's the adjacent side of this triangle, and we know the hypotenuse, so we would use our cosine function. So the cosine of 22 degrees equals the adjacent side, which is the horizontal velocity, divided by the hypotenuse, 18.4. And then we can multiply both sides by 18.4 in order to get that horizontal velocity. So let's go ahead and do that one together. We'll set up the vertical side, but I don't know if we really need to solve for both of those. Yeah, I heard somebody say like 17 point something. That's what I'm getting. 17.06 meters per second. If you're getting something different, check that you're in degree mode and not radian mode. And then if we could also find the vertical side of that triangle, that's the opposite side, we would still want to use the hypotenuse, so we'd probably want to use our sine function if we wanted to get the initial vertical velocity as well. And I don't know that we need to do that one, right? We just multiply 18.4 times the sine of 22. No big deal, right? We can do that. So that's something that we're going to need to do probably for these projectile problems that are launched at an angle. So we already reviewed that. I believe we did say last week that for this special type of problem where we're starting and stopping on the ground, that the initial vertical velocity and the final vertical velocity are the same thing, except the final vertical velocity is negative. We just saw that with problem number 41. One other thing which won't really come into play is it does take the same amount of time to go up to the top of the trajectory as it does to come back down to where we started. I'm not really going to write that in an equation form, but the rate at which Earth takes away the upward speed is the same as the rate at which it gives back the downward speed, 9.81 meters per second squared. So I would like to solve one of these with you guys and then give you, I don't know, we'll probably have time to do maybe one in your foursomes. But you know, even if we need to answer some follow-up questions about this afterwards, that's fine. So here we have a softball. It's hit by a batter, and I give you the initial velocity, similar to what we just saw for the soccer ball. A fielder catches the softball at the same height that it was hit from. How far did that thing travel? Right? How far did it travel from the time it was hit until the time it was caught? An assumption, well, not an assumption. We're being told that it's caught at the same height that it's hit from. I'm going to pretend that it was hit from the ground and caught on the ground. I think that simplifies things slightly. All right, so if you didn't do it already, set yourself up 2 columns of variables. If you have one from when I reviewed the 7 that we know, that's great. You can just use that one.